Okay, very good morning, class. So we'll continue from chapter 2. So yesterday what we saw is the components of, we actually went into in detail about assembly program. So first we saw on the components of assembly program, just to recap what we actually learned yesterday night. So we saw that the assembly program has three components. The first one is assembler directives. The second one is actually the assembly language instruction and the commands. Now I've already showed you yesterday using MPLAB. And then we took one assembly language statement, how many fields maximum one statement can have, that the first column must have label, the second column we must have mnemonics, the third operand, and the fourth is command. And then we went into in detail about each of the assembly language statement, what is the requirement for the label. It must start from the column 1, the first column, that means the most left hand side margin. Must start, and then how do you actually separate it from the second column? Is always by at least minimum a space, a tab, colon, or sometimes end of line. So we have seen all this requirement. Then we saw what is mnemonic, and the operand field, and the command field. And then out of the three components, we actually, of course, throughout our course, we are actually learning the assembly language instructions one by one. And the command is actually relatively easy. So the third component of the assembly program is actually assembler directives. Now, as I mentioned earlier or yesterday, that assembler directives is actually keywords or something similar to instruction, whereby it is used to control the flow of the program. So we have few types of assembler directives: control, data, listing, macro, and also object file directives. So yesterday we saw into few of control directives. We saw if, else, and if. So this is the code actually that we saw yesterday. So don't worry, I'll actually share this code with all of you. And then we saw the second one is end. End is another control directive. It actually controls when the program should end. Some of the control directives we won't be using, so that's why I'm not going through them. So hash include, as I mentioned, is the beginning of the program where you want to include the file directives. And then you have the radix. I think we stopped at radix, right? So radix actually sets the default radix or the base number for data expression. As I mentioned earlier, if you are using radix, what happens? Any data or any number, for example, even the address, if you are not using prefix, any number without prefix will fall under this radix. If you set radix hex, that means whatever number here, here, and here, this one, and this one, which doesn't have prefix in front of it, all these numbers will be considered as hex. Of course, as I mentioned earlier, if you write the prefix like this, then it will override the radix. Is it okay? Any question up to this point? Yes, no? So another data directive is while and while. So this is another data directive. This is like a do while loop. So you have while, you have the expression. While the expression is true, you will keep running. So let's say, for example, yesterday's one. So I'll just
So get the information from the
Okay, the while expression I'm having error is saying I must finish within 256 iteration. So actually it's not 256. So I'll check back on that. So the expression should be something like this. So while the version is actually, the expression is here, as long as the expression is true, then it will actually execute this instruction. So this is the while and while. Earlier we saw is actually the if and also the if else. So these are known as the control directives because they control how the program works. Basically this is nothing but, this is a if else statement. It controls either one of the condition. The other one is a continuous loop. It actually will keep looping. The reason why I have error just now is when I put the expression like this, version is equal to D1, the expression is true, right? So what happens is, this and while it will continue infinite loop. It has infinite loop. So when I actually compile this, it has an error. It says must terminate within 256 iteration. The reason why I'm having the error is I should have another instruction here to control this value. I should use a loop counter. Let's say I put a condition here while the version is not equals to 0. It would be more sense like that. While version is not equal to 0, I do like this. And inside here, initially version should have a value, and then I should minus the content of the version. So when the version is actually minus, the point when it reaches 0, it will come out of this while loop. Now currently, the expression that I wrote here, this one, I'm not writing any instructions to, anyway this condition, if I do like this, it will be infinite loop. While and while loop, you cannot make it as infinite loop. It must be within 256 iteration. So that means later on we'll see in chapter 2, we'll see how do we actually have an infinite loop and also a finite loop. So in this case here, it will be much more better if I write version, while version is not equals to 0. Not equal to 0 means will be not equals to 0. Then let's say here version is equals to version equals 100, and here I must write an instruction to decrease the version during every iteration. I should decrease it by 1. So that means this whole loop will run for 100 times. When after the 100 time, what happened to the content of version? It will become 0. So immediately it will loop out. So when you do like that, then you won't have error. Now we're having error because it is running infinite. It's running more than 256 times. So that is the control directives. So we have learned few control directives. The next one is you're going to learn about the data directives. So there are few types of data directives. You have DB. DB means defined by. DW means defined word. And also set and EQU. So what is actually DB? This DB and DW is actually used to store storage in program memory. This data directive DB and DW so just remove this. The DB and DW data directives are actually used to store data in program memory. So how do you actually use them? Is you can put DB. Later we'll learn why we need to actually store the values in program memory. Now sometimes, just for a simple example on why we actually need to store data in program memory is that the nature of program memory is, even though when you turn off the power, the content still remains the same, right? So for example, let's say if you have an door entry system. Have you seen the door entry system which has the LCD or something like that? Let's say for example, it says that, okay, welcome, please enter password. There's some character, right? Please enter password. So even though there's a power cut, of course, usually most of the security system will have a backup power. Now let's say it's a lousy company who installed, there is no backup power. When the power is cut, of course, everything goes off. But when you on back, do you see the character comes back again? Please enter password. Now that character, the please enter the password, is actually must be stored in the program memory. Not necessarily program memory, can also be stored in external EEPROM. But the nature is you must store it in a ROM, because when the power is off, the character is still there. So you can also do that with microcontroller. You can store certain characters or certain data in the program memory, so that when you turn it on back, you can always retrieve back the data. If you store in data memory, when the moment you turn off the power in on back, all the values will be gone. So let's say you want always to display welcome, please enter password, that message. So what do? You store those characters, welcome, please enter password, that character, into program memory. So that when you on, what the program memory will do is, it will actually take the value from the program memory and it will actually send it out to display. So therefore, even though the power is cut, always that character is never lost. So I'm just giving a crude example on the reason why we need to store some data in program memory, because it doesn't disappear. Now the next thing is, how do we actually store data or characters in program memory is by using these data directives. So data directives mean it actually assigns how the data should be stored. So we have two data directives that we will be using to store data in program memory. The first one is defined by DB. The second one is defined word. So let me just show you. An example here. So this is DB. Okay, ignore the label part. So you can either store values like this, or you can also store characters like this. And what is this comma 0? This is to show that this is the end of that character or end of the sentence. So defined byte means you can only store, you are defining a byte, 1 byte number. So let's say if you want to store a value here, 2, 3, 4, 5, 6, 6. Okay, so I have used the defined byte. So when I compile this, okay, how do I know whether I've stored this or not? What did I mention about this? Where is this stored? In program memory, right? So let's go to view program memory. So this is your program memory. So there are three options bottom here: opcode, hex, machine, and also symbolic. So let us actually use the symbolic. Symbolic means you can see where is the label. A bit on program memory. So this is your display of your program memory. You can see what is stored at every address. Now take note that the address is actually skipping by 1. Can you all see? It is actually 0, 2. Then you may ask, why the address is only 4? It's supposed to be 6, right? Actually the front 2 is not written here. So as you can see, the address is skipping by 1, 0, 0 and 0, 2, 4, 6, 8. It's skipping by 2. So this is, what did I mention about address 0? It's actually the reset vector, right? That's why whenever you press F6, it actually points at this address. But what is at this address? Do you remember yesterday? The origin? What does origin do? Origin actually, what is this data? What this control directive do? This data directive. It actually assigns the line after this in this address, right? So that's why you can see. Where is my window? That's why you can see the go to start is actually at address 0. Now let's see if I change this to. To 2. Where do you think this go to start will be stored? That's right. Sometimes if you see your window is not here, you just go to window, you can open back. So you see, actually start from 002. So you understand on the origin? So we'll change it back. So do you see when you reset, the PC is actually pointing at address 00. But then, of course, take note that at address 08, do you see this one? There is an instruction, right? RETFIE. And then at address 18, there is RETFIE also. Now take note that there is a reason for this. We will see in chapter 6. So for now, these addresses are reserved, 08 and 18. They are reserved for RETFIE, RETFIE. So just for now, what you need to know is these two addresses are reserved for this. So what we usually write, why don't we actually start the program straight away from here, is because of these two fellas. this 08 and also 18 is actually reserved for interrupt. So that's why we cannot start our program straight away from 0, because here we need to allocate this portion for interrupt. Now just imagine you write few lines here, then you skip, then you write another few lines here. So it doesn't make much sense. So the normal conventional way is, after this reserved address, you start your program. So this is the last line of the program, right? You see, red 5 is address 1A. Now one instruction is how many bits? Minimum 16. 16 will take how many locations? Will take 2 locations. So that's why 18 and 19. After 19 is what? What is after 19? 1A. So 1A is where you have your first instruction. The first instruction here is, of course, is no operation. So therefore you can see no operation here. And then you have used the label here. That means the first instruction is tagged to the label start. So when you execute F7 here, your arrow will straight away go to the label start. You see? It goes to the label start. Can you follow? Now let's make this one a bit simple. Okay, just for a simple example so that you can see how the arrangement of the program memory is. Let me take this one. Let's see this one there. So at address 00 you have go to start, and then as I mentioned earlier, these 2 addresses are reserved. So our program will actually start after this instruction. So what is the next instruction after RETFIE? Move LW, right? You see that after this address, at address 18 and 19 is stored the instruction for RETFIE. After that, at address 1A, what is the instruction you have? Move LW hex 20. And this instruction is actually on the same line as this start. So that means this label is actually tagged to this instruction. Do you get it? So this instruction move LW is also 16-bit, right? So it will occupy the space 1A and 1B. So if you want to see, you can see from here. This is 1A. This is 1A. 1A and 1B. 1A will occupy hex 20. 1B will occupy 0E. So this 0E20 is actually the machine code for move LW. You can also see the machine code here. There, opcode. This label. You see it's 0E20. So that means 20 is actually stored in 1A. 0E is stored in 1B. This one is 1C, 1D, 1E, 1F. You know how to read this now? Any question up to this point? Anything not clear? Do you understand how to see this one? So after this last instruction, we have start right, move LW. After this is what? Move F. Move F, right? After this instruction, move LW is move F. This is the machine code for move F. 6E00, and you store at 001C is the address you store. Is this taken into consideration, this part here? this thing doesn't even exist because it is commented. Then you may ask, what is this? We never write this instruction also. What is this? And what is this? We never write any instruction. This is actually not instruction we write. Actually, this is, we are interested in here. Do you see this value? 2, 3, 4, 5, 6, 6, 9, 8. Have you seen this value before? Here, this one. We actually use DB. This DB will store after, what is the last instruction? This one, right? Which is here, move dash W. After this address, whenever you put DB, what it does is, after this address, it will actually store these values. So that means the last address it stored, the last instruction is 1C and 1D. That means from 1E onwards, it will store the values. So that's why at 1E you can see 2, 3. At 1F you can see 4, 5. At 2, 0 you can see 6, 6. At 2, 1 you can see 9, 8. So because we are actually storing this value, but what the compiler does is, whatever value that you store here, it tends to translate it into equivalent assembly language. That's why you get some rubbish here. This one, do you understand? VCF, RBX, 0D, some sounds like a bomb like that. So this two is actually a translated version of this. Actually, this instruction doesn't exist. I mean this RXB0D0. Why we get some funny things like this is because whatever data that we write here, the compiler tends to translate it into equivalent code. So that's why you get some value. So don't be disturbed by this. The actual thing is we are interested in this. This is what we store. You follow? So this is DB. We have actually stored value. We can also see here. So this is the last instruction. After that is what? 2, 3, 4, 5, 6, 6, 9, 8. That means you managed to store your data. You can create your own database there. Is it okay? Sometimes, let's say if you want to do data logger, you want to store the captured temperature, you can either store in program memory, but usually in the microcontroller there is also EEPROM. So whenever you do data logging, you can actually program it to store it in EEPROM. So what happens is later when you want to extract back the data, EEPROM is a ROM, so you can extract back the data. So same principle also you can actually do in program memory, because program memory is a ROM, it's a flash memory, remember? So you can store some values inside, and even though if the power is off, on back, the value will still be there. So for now, we will actually learn how to store. Later on in chapter 2, we'll see how to extract them back. Is it okay? Okay or not okay?
Okay.
So we have seen how to store value. Let's see how to store. What do you want me to type? I thought so. So can you see the micro P is easy here? You can't see it here. Actually, the last instruction is this one, right? Move WF. After this, got something else. Or actually, what is this? This is actually ASCII. You have learned ASCII, right? So if you want to see the ASCII, you go to opcode hex. You can see here. Fine. Micro P is easy. So what this one do is, whatever code that you write, if it is actually ASCII can be translated into ASCII, what it does, it displays the ASCII message here. So you can actually know that 4D is actually I, 69 is actually M, 63 is actually C, R, and then there's a space, 70 is a space, I think. Something like that, I also forgot ASCII code. But ASCII code is how many bits? One character of ASCII, one character is how many bits?
2 bit.
Huh? 2. ASCII bit is how many bits? 16. ASCII bit is 7 bits lah. One character is actually 7 bits. So, okay, so 4D is actually, the lower byte is M, 69 is I, 63 is C, 72 is R, 6F is O, 70 is P. After P is what?
Space.
Space is 20, X20. After again is 69 is I, 73 is S, 20 is space, 65 is E, 61 is A, 73 is S, 79 is Y. So, because ASCII is actually it's only 7 bits. So you'll notice that on the second digit of the single byte will never go more than 7, because it's 7 bits. It's not 8 bits. Okay, but still with 7 bits you can represent with 2 hex digit number, right? Only thing is the second digit, which is like 4 or the 6, will never go more than 7. The maximum value you can go is 7. You see all the, do you understand? You can never go because it's 7 digit. So you can also store. So for example, just now the message welcome, you can also store it here. And then whenever your microcontroller starts, what you can do? You can extract it from the program memory and display in the LCD. So you can display this character. Is it okay? What's the time now? 8:46. So this is defined byte. Defined byte means you store whatever value here in a byte. That's what it means. Of course, defined byte ASCII codes are stored in byte. Each character is 1 byte, right? So it is stored in byte. And just now the value that we store also, all those values are actually a single byte value. So in our next class, we'll see the difference between defined word and defined byte. So whatever code that I've tried here, I will actually share it and will send all to you. Yes, Gideon.
Why is it like a copy is easy, then there's a colon, 0.
Oh, this is to show that this is the end of the statement. But this is not necessary also. We actually do that to actually, when you want to process time, when you see the zeros just now, it will indicate that, okay, that is the end of the line. So if you don't put that, then straight away it will just end abruptly like this. That's all. Then of course you may see why there is an N here. We never wrote N. Before the M, there is an N. Why there is an N? I didn't put the N. Remember what I told you? Anything that you write here, if it makes sense, if it can be translated into ASCII character, it will display here. So that means the 6E is actually N. 6E. This actually 6E00 is our move WF, right? But this whole part here is ASCII. That means whatever value that can be translated into ASCII will be displayed here. So coincidentally, that 6E is also an ASCII code for N. So that's why you have N. Understand?